Okay, so now we're live. Um, the first thing, I just want to show you where everything is. I mean, I recognize a bunch of faces, so the people who have taken Normandale classes before all know what D2L is and how to get around. But to get to D2L is going to be where everything in this class is posted. Anytime there's new information or whatever, it'll be posted in D2L. So get in the habit of checking that regularly. Go to the main Normandale webpage, and if you go to the drop-down menu, current students, D2L is the first thing that pops up here. And when you log in with your star ID and everything, you get a list of the classes you're taking the current term, or you can look back at other semesters and stuff too. But this is statics. And if you open up the statics thing, the first thing you see is announcements. And that's what you should check every day. If I put up something new that you need to know, it's going to be in announcements, or there's going to be a reference to it in announcements. Then there's some other stuff that we'll talk about. Assignments, that's where you're going to submit your work. So the way you're going to do work is you're going to do it pencil and paper, and then you're going to scan it or take a picture of it and then send me a PDF of it. And that'll all be in assignments. Your grades will be updated here. But I want to talk about the syllabus today, and all the other materials are under content. So, okay, when you open up the content section, you'll see this. And of course, I have not loaded the syllabus here, but I should have. I do have the syllabus. Let's pretend it's there. It would be under course information. Can you just keep that name thing moving around, anybody who comes in? That's just sort of a memory device for me to remember names. Okay, so this is the syllabus for this class. Let's pretend that it's in D2L and not in my folder, which you can't access. So this is statics. It's a 3-credit class. And the first thing I want to talk about is just the time commitment for this class. And this is important because Normandale does all their summer classes in a condensed format. And so that means a lot more work. You might think like, well, I don't want that. I want a condensed format where I do the same amount of work, but it's just 5 weeks instead of 16 weeks. But it doesn't work that way. Okay. I mean, maybe if you think about it, you can understand why. So here's how the math breaks down. That was supposed to be funny, but 3-credit class, 16 times 3. So 3 class hours a week for 16 weeks gives you 48 hours of class instruction for a class. Okay. Well, we only have 5 weeks. So divide 48 by 5, and you end up with about 10 hours of class time, somewhere in that ballpark, of instruction time. And then about 19 hours of work outside of class, which is just a pretty standard multiply the class time by 2. If you look that up online, every college and university will give you a guideline for how much time you should expect to spend outside of class for every hour in class. And that guideline will say 2 to 3 hours. It'll say that at MIT, and it'll say that at, wherever. So 2 to 3 hours, that's just standard. I'm going based on 2 hours here. So this is sort of like the low end. Okay. But this class, if you think about the math this way, is going to require somewhere in the ballpark of 29 hours a week as kind of a low, the low end. And I think probably most people, if you spend about 29 hours a week in this class, it'll go well. I don't think you're going to find that this class takes a ton more than that. Some engineering classes do take a ton more than that, but I don't think you'll find this one does. But I just want you to recognize that that's a major time commitment. And so these summer classes are not designed for people to work full time and take these classes. I'm not saying it's impossible, but I don't recommend it overall to the average person. And so just before you spend a ton of money and a ton of time and things go badly, just think about whether you're able to commit this amount of time to this class. Okay. And if you want to talk about it, I'm happy to talk about it individually. So now the way to contact me, this is my contact information. Please just call me Gaio. My office is, that's my old office. I need to adjust that. This is not my office. My office is just kind of across the hall here. It's 1311. You can contact me through email. I have a phone number where I can pick up phone messages, but I don't actually have a physical phone in my office. So you can't talk to me instantly this way, but I can get those messages and get back to you. The best way to contact me is to use the instant messenger in D2L. So let me show you that. So anywhere you are in D2L, there's an icon up at the top of a letter, and that's the instant messenger. And if you go there, you can send out messages. This is nice because it keeps it all organized for me. Email will work too, but the instant messenger just works a little better for me. It's harder for me to overlook messages because I have less stuff coming in. Everything that's coming in is from students, so and then class information, class time is now. And this is going to be the room number all the time. My office hours are going to be from 1 to 3 on the days that we have class meetings. And that is going to be just down the hall in room S1320. So the way that works is we have this class, then we have an hour for lunch or whatever, and then we have this. If you're in a hurry, if that doesn't work well for you, I'm happy to meet between class and this, but that's just sort of my default mode if you don't have any special preference. The prerequisites for this class are Physics 1, Calc-based Physics 1, and Calculus 1. And the materials you need for this class, you need some kind of graphing calculator that does vector calculations. TI calculators, the TI graphing calculators all work really well, but you can use, if you have an HP calculator or something, that works fine. And I will try to, as we go in this class, I'll try to point out how to do certain things based, for the different TI calculators. I don't really know HP calculators, but I can help you figure that out. And AI is so nice for that kind of stuff now. You can go to ChatGPT or whatever you like and ask it a question, how do I enter a vector in my HP whatever calculator, and it'll tell you. And it's pretty much always right about that stuff. By the way, if you go down here under content, there's a lot of stuff. There's where the assignments are going to be posted, solutions to assignment problems. There's all this stuff. One of the things here is I have it twice. Let me get rid of one of these. It says statics text. And I teach this class in a sort of a different, some of the notation I use, some of the formatting I use, the ways I ask you to think about this stuff in some ways is different from the way you would see it in a standard statics textbook. I think you'll find this way works really well. I think it prepares you well for going to the U or wherever you're thinking of transferring to. So you don't have to worry about it not being compatible or something. But it does mean that if you get another statics textbook, you have to translate a lot of the stuff that they tell you into sort of my notation and stuff. I think if you want to look at stuff in a textbook format, you'd be better off going to this statics textbook. It doesn't cover every single topic we do in this class, but all the big ones in quite a bit of detail. This is something I wrote on a sabbatical, and it's broken up into categories: matrix math, vector review, all this stuff. And so this information is here, let's just look at it. So it's all sort of wordy text format with examples telling you how to go through the steps, all that stuff. But the reason I'm bringing this up now is also there are appendices that tell you how to do a bunch of the calculations we'll need in this class on various TI calculators. So like if you wanted to multiply matrices, we won't do that too much in this class, but it tells you how to do it in a TI-84 with figures, TI-86, TI-89, and then TI-Nspire. So if you're trying to figure out how to do any of these calculations in your calculator, remember that this is here as a resource. And also some programs that you can enter to make some calculations easier, so you don't have to, so it's not as many button clicks to do the calculations. If you enter this program once, then it's pretty easy to, like an example is for a TI-84, it'll tell you it doesn't have a built-in cross product function. We'll use cross products all the time, but this will tell you how to enter a cross product function. That'll be helpful in this class, and then it'll be helpful in future classes too. Okay, so that's just all a wordy, long-winded way of saying that you need some kind of graphing calculator. Recommended reference books. I actually don't recommend getting an outside textbook for the class itself. These might be helpful for future reference later on. I really just have these in here, so if anybody's transferring to universities that aren't accustomed to taking our transfer students, they might want to look at your syllabus, and this tells them, what kind of material we cover. So that's really what that's in here for. But these are both good books. This is the textbook they use at the University of Minnesota. And then Sham's outlines are always great. They cost $20 or something like that. It might be more than that now. It was $20 when I was a young man full of motivation. But they're like paperback things that give real concise little descriptions of all the topics, assuming that you've already done it before, so it's not as long-winded. And then they give a ton of problems for you to work on, and solutions and answers to those problems. These Sham's outlines are really helpful if you end up taking a standardized test like the Fundamentals of Engineering exam. This is a great resource for preparing for that. Also, I say it's $20, $30, whatever, but in a lot of cases, you can find PDFs online of these that are just being given out. So, it can be free online. The topics we're going to cover, we're going to start with a vector review. Then we're going to get into statics of particles. Then we're going to get into rigid body statics. So in physics 1, you probably spent most of the time on particles. And then right towards the end of the semester, you covered rigid body physics, which is when you talked about moments, or if it was a physics person rather than an engineering person teaching it, they probably called it torques, or often called it torques. Engineering people tend to call them moments because the word torque is reserved for a specific application of moments. And then we will talk about really what the heart of this class is not just doing the physics of a single rigid body, but connecting a bunch of rigid bodies by joints and doing the physics of those. It's called structures when you have a static thing that has multiple pieces connected by joints. And we'll be able to do things like calculate the reaction loads that each member is applying to the adjacent member, which has, pretty easy to understand applications to engineering. If you need to know how strong this thing has to be that's here in this big connection of rigid bodies, you can use these techniques to calculate that. It's useful in engines, machines, in civil engineering. It's useful in bridge design and building design. So that's really, I think if you went to 100 statics professors and asked them to give you one problem to test your knowledge of statics, 90 of those 100 would give you a structures problem. That's what this class is mostly about. But then we'll talk about internal loads, which is kind of a first step into starting to understand stress and strain analysis. And then right at the end, we'll do a little bit about some types of friction. The grading scale that I'm going to use is probably just going to be 90, 80, 70, 60. It might be curved a little, but it usually isn't. Usually those grades end up being pretty good. It won't go any higher than that, So if the whole class scores 92 and above or whatever, then everyone in the class will get an A. But if nobody in the class gets above 90, then it's likely it'll get curved down a little bit. It usually doesn't happen, though. Your grade for this class is going to be broken down this way. Let me add these up real quick. Yep, 100. So these all add up. Hi. So it's going from the things that are valued the least to the things that are valued the most. The first one is this thing, professionalism, consistency, and appropriateness. I'm gonna just list out what these things are, and then I'll go in more detail after I'm done. But 5% of your grade is that. 5% of your grade is lecture quizzes. 10% is daily assignments. 10% is weekly assignments. And then 70% is exams. And we're going to have 4 of those exams. These daily assignments are only given 10% of your grade, but really what's going to determine how you do in this class is how well you understand these daily assignments. So I'm not giving it a ton of points because, it's obviously now it's easy to just go online and get good solutions to all these problems. And that doesn't do you any good to show me that you know how to use ChatGPT or whatever. But this is really the heart of the class. If you get to the point where you understand how to do all of the daily assignment problems that I give you, and you understand it well enough that somebody could ask you questions. Why do you do this? Why do you do this? You could kind of explain it. Then you'll do great in this class. Anybody have any questions? I guess I haven't been asking for questions yet, but anything that we've covered so far before we start getting into what these different categories of the grade of the class are? Yeah.
How much of dynamics transfer over to this?
So much of the way I do dynamics is the way I do statics. So a lot of it is going to transfer over. It's less mathy than dynamics because you don't have to deal with derivatives for the most part, because we don't have to deal with accelerations. Accelerations are always zero in statics. But you'll be very, like all the stuff that you're used to with those moment tables for rigid bodies and everything, it's going to look very familiar. Any other questions? Yes.
So I think I read that this class only is in person for this week. Is that correct?
No. This class is, here are the class meetings. Well, no, the class meetings are every Tuesday and Thursday for 5 weeks. And once we get going, so 2 weeks from today is going to be the first exam. And then after that, we're going to have our exams every Thursday at our class meeting. And then every Tuesday is going to be, well, I'll tell you what the structure of those classes are going to be when we get to that in the syllabus. Okay.
Yeah, I think online it mentions like after the first week, it's like hybrid. Like you're required to be here for the first week, but after that you can like essentially work through stuff.
Okay.
Lectures and everything like that. I think that's maybe what you're.
Let me look at what that says. That's students must attend the first week. That's okay. So what that's trying to say is you can get dropped from the class if you don't show up the first week. But this class is designed to be in person on Tuesdays and Thursdays. But if you add that up, that's a total of 20 hours of in-person time, which is not enough for a 3-credit class. And so there's going to be additional like lecture videos posted. Okay. Any other questions? So if being here on Tuesdays and Thursdays is hard for you, we should talk about it. I mean, this class is really designed for you to be here every Tuesday and Thursday for 5 weeks from 10 to noon. Yes.
So is there like no final or?
Just the 4th exam is the final. And all of the exams are going to be cumulative anyways. So each exam is sort of like a final up to that point in the class, you know. And the 4th exam isn't weighted any more heavily than the other ones. Any other questions? Okay, so let's get into what these categories are. So the first one, this is 5% of your grade. It's not a big thing, but I call it professionalism, consistency, and appropriateness. I think to describe it in like one sentence, I would say this is really just me measuring how well you're making an effort to communicate and do your work in sort of a like semi-professional manner, you know? So it says here, these classes, like, yes, they are about teaching these mathematical techniques, and that stuff is very important. But it's also important to come out of engineering school ready to work in a professional environment. People are expecting that. Your employers are expecting that. And so, I mean, I expect you to be trying to be here on time, trying to communicate with me when you can't be here, when weird things come up, if you can't get your assignment in. I expect clear communication. I expect you to read instructions carefully enough that if I ask for a specific file type, you turn your stuff in with a specific file type. If I ask you to turn things into a specific folder, that you do that. All of that stuff is just part of being a good, you know, student and in the future a good employee. Okay. So the list of all the things that I consider for this are here. Attendance, punctuality, turning stuff in on time. You know, everybody sometimes needs a little extra time to turn stuff in. But if it's a consistent pattern of getting stuff in late, then, you know, I'll take it and I'll grade it or whatever, but that's not ideal. And that's not the kind of habits that I'm trying to build. You know what I mean? I've had students in the past show up for tests multiple times without pencils and without calculators, like all that stuff. Just present yourself in a way that makes people want to work with you, you know? If you use the OSD office, get me those forms ahead of time, have them filled out. The parts that you fill out, have them filled out. Reasonable lobbying for grades is like, you know, if you feel like I made a mistake on grading something, I'm happy to talk about it, of course. Like, I want to get stuff right. But if part of your strategy for getting a good grade in your classes is just consistently trying to wear your professors down based on, you know, like, what about this? Could I have gotten one more point here? Maybe this could, like, nobody wants that. And that's just not being a respectful student, you know? Anybody have any questions about that? By the way, I mean, so I sort of take notes as we go through the semester with this stuff. And at the end of the semester, I'll give you your score for this, which for half the class or more is just 100% for this, you know, like everything's good. But I do try to give you feedback on this on D2L. If I give you a score for this that's below 100%, then I'll tell you why. And I would really recommend, if that happens, read that stuff and think about it, you know? And it's really there to help you become better. Well, and it's there to encourage you to let me remain a sane person. Then the next 5% chunk of your grade is lecture quizzes. So quizzes are distinct from exams, and this is the difference between them. So the quizzes are short, and all they are is short answer questions about stuff that I've said in the lectures. And I try to focus on the big things. I'm not trying to catch you on real, like, unimportant details or anything, but I'm just trying to get you in the habit of not just taking notes in class, but going back periodically and reading your notes and trying to understand what I said and understanding how the parts fit together, you know? I think, to me, a good engineering student, by the time the semester is over, they're like, there's wrinkles and fingerprints and stuff all over your notes because you keep going back and back and back, you know? It's not just about like getting to the point where you understand it. It's about continuing to refresh your memory on it to the point that it's part of the way you think about this stuff. Okay, so these are just, say, 5 to 10 minute short answer question things. asking you to tell me about stuff that I've said in class. And often when I say the things that I want you to focus on, I'll say, I'll let you know that these are key things that I want you to have as part of your sort of memory bank. And then I'll try to emphasize those on these quizzes. Just like the exams, these are cumulative. So it's not, a quiz isn't just going to be on material since the last quiz. I want you to go back to the beginning and reread stuff and reskim your notes and everything. I want this to, in an ideal world, I want you to remember everything I said in class from the start of the class to the end of the class. There's a reason that I'm saying this stuff. And it's not just because they say I have to talk for a certain amount of time. It's because it helps you understand what you need to then go and work on these problems in a reasonable way, in a thoughtful way. Any questions about the quizzes? Okay, and then 10% of your grade is daily assignments. So I have the schedule down below here on the syllabus, but basically every weekday, Monday through Friday, I will give you problems to work on, and you'll work on those pencil and paper, turn in PDFs of them, and I'm gonna give you my solutions to about half of those problems. So if you get stuck, you can go look at my solution and get yourself unstuck. But these are really, like I said, these daily problems are the key to the whole class. If you understand those well, then you'll understand how to do the exam questions well, and you'll do well in the class. The ones that I don't have solutions posted to, during our class meetings, I'd be happy to do, if you have questions about those, tell me like, okay, can you show me how to do number 6 or whatever? And I'll go through that on the board, on the fake board. And this 10%, I'm not grading these. I'm not going through and making sure that you do them right. Ideally, I would do that, but it just would take too much time. But the solutions are available. The ones that don't have solutions available, I'd be happy to tell you how to do them. And it's just your job to understand how to do them. By the way, to understand these problems well, you might think like, oh, well, I'm not gonna try to do it if the solutions are there. I'll just understand what's going on from the solutions. Well, you're welcome to do that, but it turns out that just doesn't work very well. And if it worked well, I would tell you it worked well, and that's what I would have you do. But in order to learn this material, you have to struggle with these problems. That's just the only way to do it. And so try to do these daily problems on your own. If you get stuck and you can't get yourself unstuck, look at the solutions or ask me, get unstuck, then try to do it again. I think the people who do best in this class will do these problems when they're assigned, and then a week later they'll go back and redo them again, or at least like sort of go through a kind of outline of the process of doing this. All of this is just about building that muscle memory and just reinforcing these memories, So the grade on this is just basically checking off like, yes, this assignment was turned in, this assignment was turned in. And that's what differentiates these daily assignments from the weekly assignments. The weekly assignments are like the same kind of problems as these, but I don't give you the solutions for them. And I will grade them the same way I grade exam questions. So I'll give you feedback on these weekly assignments that you can use to determine like, am I, writing out enough of the steps of these problems? Am I thinking about it right? That kind of thing. This is really just a way for me to give you feedback without giving you feedback on every single problem you do, you know. That's also 10% of your grade. Any questions about the homework assignments? And it says weekly, but I call them weekly. I mean, that might be pretty close to right. One of those a week. That would be 5 of those. That's probably a reasonable guess for how many of those I'll give you. And next is the exams. There's 4 of them. Each one is worth 17.5% of your grade. And each one of these exams is going to be cumulative up to the point of that exam. So exam 3, for example, will still have questions on it from the first week or whatever. As you're preparing for these exams, you need to refresh your memory on the old stuff too. And these, the quizzes are just short answer questions about stuff I said in class. The exams are all calculations, and they're all calculations of the type that I'm giving you on those daily assignments. So if you understand the daily assignments well, you'll look at these and they'll look very familiar and you'll know just how to go about it. Okay. The processes I'm teaching and the processes I'm asking you to follow in the daily and weekly assignments are the same. I'm not asking for any off the wall stuff on the exams. Okay, there is one thing that makes exam 4 a little different than the other ones. You can use exam 4 as kind of a mulligan score on one of your first 3 exams. So, for example, like say you don't score very well on exam 2, then if you score higher on exam 4 counts as itself, and it also replaces the score for exam 2. Okay, so you can have one exam that goes badly without it affecting your grade. That also functions if you miss an exam that we haven't talked about before the exam, like if you just don't make it to one of the exams, then for the time being you get a 0 on that, but then when you take exam 4, that score replaces the 0. Okay. And the test schedule is here. Oh, it's not 2 weeks, it's next week. Yeah, everything comes so fast in the summer. So our first exam is going to be next Tuesday. Okay. And then after that, it's going to be all Thursdays. And then the class schedule. So we skipped yesterday. Today, we're going over the syllabus and vector review. Each day of the week, each work day of the week, I'm going to assign problems. And yeah, that's my plan. If anybody is interested, I could give you, I don't think I can give you exactly what problems are going to be assigned for the week, but I could give you a good guess of what problems will be assigned for the week, so you could sort of work ahead if you wanted to. So let me know if that would be helpful to you. And yeah, my plan is it's 5 weeks. That makes it hard for this stuff to stick well in your memory. And so I'm going to do my best to stick it in your memory by having you do a little work every day, basically. and just keeping you on a 5-day-a-week schedule of this stuff. Anybody have any questions about that? Yes. You can see them all beforehand, and if you want to know which ones are going to be assigned for the week, I can give you a very good guess at what it's going to be, although it might be off by a question or two at the beginning or the end or whatever. Basically all of the questions are up right now. I mean, if you go to content and go to assignments, this is all the daily assignments. I think there might be a couple that I need to update this semester. Usually there are, but like for example, so let's see what rigid body statics problems look like. These are the problems that the daily assignments are going to be made out of. And then the solutions are assignment solutions right here. So then if you look at this and you're like, I don't know how to do that, then go to rigid body static solutions. And if you're lucky, the number that you don't know how to do is one of these ones that I have a solution posted for. If you're unlucky, then just write it down in your notebook. And the next time we meet in class, say you'd like to see number 8 or whatever, and I'll do it. And most of it, I think almost always, if you have a question on how to do something, you're not the only one. So everyone will be happy to see it. And even the people who feel like they did it right will be happy to see whether they did it right. People can compare their notes to it. So. Any other questions right now? Yeah.
When a daily assignment's assigned, is it due that night?
Let's see. So I will assign something tonight, and it will be due by midnight tomorrow night.
Good day.
Yeah. So yeah, and it'll always be. And by the way, I would recommend. So the deadlines are always going to be 11:59 p.m. But as much as you can, I would recommend trying to work on stuff before class, because the next class is going to use that material. And so it kind of piggybacks on that knowledge. It just feels a little like it's harder to make it stick in your head if you haven't spent time with that material when the next class happens. It's not a major thing, but I think it is a good habit to get into. Any other questions? Okay, and then by August 6th, we're going to be done. So it's pretty fast. Okay, so I don't know. The world has changed in school, that's for sure. So cheating used to mean like students would take labels off their water bottle and then write stuff in small text and then put it back in their water bottle. It was really like people came up with some great stuff, I almost felt bad giving them the F and putting the letter in their permanent file and everything. But now cheating is so boring. It's just AI. But for the daily assignments, and actually I didn't mention that with the daily assignments that I don't have solutions for. AI will give you solutions to all this stuff. And if you want to use AI to give you solutions on the ones that I haven't posted solutions for on the daily assignments, feel free to do that. They won't use the notation I use, so there'll be a little bit of translation you have to do. They won't use the steps, the method that I use or whatever, but it'll be the same. The meaning will all be the same. But no AI on any of the stuff that's evaluated. So don't use AI on the weekly assignment problems, or exams are going to be in class, but obviously don't use AI on exams or quizzes or anything. there is one engineering class at Normandale that's pretty much AI, free AI use, and that's Intro to Engineering Design, where you're designing products, doing robotics, stuff like that. And but really every other engineering class here and most places is largely asking you to pretend like AI doesn't exist while you learn this material, you know. And then after this point in the syllabus, everything is pretty much stuff that's just information provided by the school. So the course learning outcomes, you can look at that if you want. I don't find that super useful. And then these are all just, none of this is stuff that after the break kind of, I haven't written this stuff. This is just stuff that's supposed to be copied from the school. So some stuff on AI, code of conduct, Americans with Disabilities Act, information about the OSD office, which can be very helpful to people. Title IX statement. Yeah, and that's really the structure of the class. Anybody have any questions about any of that? Okay. Well, is everyone good to keep going? Or anybody want to take 3 minutes or something and run out and get a drink of water or anything before we get going? I'm gonna just start talking about vectors and stuff. Okay, let's do it. So, yeah, that doesn't work. So what do you think the icon for OneNote looks like? whoever recognizes OneNote on here, productivity, I'll bet. Seems likely, doesn't it? OneNote, yay. Okay, so this is statics. And this is a 2026 summer. Okay, and this is July 7th. Okay, so there is a written vector review that is going to be part of your assignment to read, but I want to just highlight some of what I think are as kind of the key points of vectors. Ben, you've already gone through this at least once, so sorry about that. But as I said, I'm a big fan of repetition, so you get the most repetition of vectors on anybody. Okay, so vectors. A vector is two things. It has two bits of information in it, a direction and a magnitude. And it doesn't have anything else in it. So it doesn't have a location, it doesn't have a rate of change of direction, anything like that. It just has these two things. Vectors don't have units on their own. They can have lots of units. So some examples of things that are represented by vectors are position, velocity, acceleration, force, and they go on and on. Momentum, angular momentum, all these things, moment. But the key thing is a vector on its own doesn't have like an identity, really. It's a mathematical object any more than a number has a unit. Those are both just mathematical things. And so the units are determined by what the vector is representing. The notation that I'm going to use in this class and in all my classes, this is a really useful notation in engineering because of the way it facilitates matrix multiplication, matrix calculations. And so like in physics, you've seen a notation like this for two-dimensional vectors. In my classes and in most engineering classes, instead of using this notation, this would be written in a matrix form like this. And a 3D vector, so you could also write this as x, y, 0, where the z is 0. Okay, these two things mean exactly the same thing. And if you're working in 3D, which we're going to do some, the equivalent of this is x, y, z written as a column matrix. One of the most common calculations that we're going to use in this class is taking a cross product of two vectors. And intuitively, what a cross product does is, the result of a cross product is, so the result is a vector that's perpendicular to both input vectors. And it obeys the right-hand rule. So we'll talk about that as we do some examples. In order to do a calculation of a cross product, there's sort of two ways you can think about it or write it down on paper. So if you're taking a cross product of a vector ABC with a vector DEF, I think probably anyone who's done cross products before, the most likely way that you've seen how to do this calculation by hand is to write out a matrix that has I, J, K in the top row. And then the second row is the first vector, A, B, C. And then the third row is the second input vector, D, E, F. And the cross product is the determinant of this matrix. Have you seen that before? So like this, the way this would work is now to take the determinant, you would have I, and you would cross out the row and the column of I. And then you would go B times F minus E times C. So multiplied by this I, you would have B, F minus E, C. And then you'd go to the next one over. And you have to remember the negative sign here. So then you'd have minus J. And you'd cross out the row and column that J are in. and you'd go this times this minus this times this. So this is A times F minus D times C. And then you'd go to the next one over, and you go plus K. And you cross out the row and column that K is on. And then you go this times this minus this times this. And so that's AE minus DB. And if you write this in my notation, then this is BF minus EC negative AF minus DC, and then positive again, AE minus DB. There's all this stuff with matrices and vectors where the Y component or the Y element or whatever has a negative sign on it, and the X and Z don't. Y just always has to be the difficult one. It's just the way vector math works. You also can think about it this way. Before I go on, does anyone have any questions about what I did there? Or you could also do this. This is the way I tend to think about it. I think it's a little faster. It skips a little writing. But if you're multiplying cross product A, B, C, D, E, F, first cross out the first one, and it's this minus this. So that is BF minus CE. Then the second element, the second component is a negative of, cross this out, and it's this times this minus this times this. So that is AF minus CD. And then the last one, cross that out, and it's this times this minus this times this. So that is AE minus BD. And obviously these two have to equal each other. It would be a problem if they didn't. But this, to me, is just a little quicker. So now here's a question. What can we say about the cross product of two vectors in the xy plane? Well, the answer is actually in part A here. The result of a cross product has to be perpendicular to both of those two vectors. So if you have two vectors that are in the plane of the board, no matter what they are, the only vectors that are perpendicular to those two are one coming out of the board or one going into the board. And so we would expect that the cross product of two vectors in the xy plane would have to only have z components. They can't have any x or y components. But let's see that just doing this calculation. So if we have, so let's say we're taking the cross product of A, B, these are in the XY plane, so the Z component is 0. And we're crossing it with C, D, 0. Okay, so first I'm going to cross these out. And we have B times 0 minus D times 0. So clearly the X component is 0. Then we'll cross out the Y components and take this times this minus this times this. Again, you have A times 0 minus 0 times C. And so this has to come out to be 0 again. And then last, we cross this one out, and it's this times this minus this times this. And so we have A, D minus B, C. So depending on what these 4 variable values are, that could be positive or negative or whatever. But what has to always happen is the only non-zero component is Z. Okay. When you do torques or moments in Physics 1, I think for most professors, you probably focused on stuff that's happening in the plane. And so you can sort of lose sight of the fact that what you're getting out of that torque or that moment is a vector. Because you're just getting a single number every time you do it. But remember that these moments are always, they're always vectors. It's just that when your moment is dealing with forces and locations that are in the XY plane, the only non-zero component is Z. One thing that I guess cross product is helpful for understanding is what is an acceptable coordinate system? As we go through this class, we're going to have to choose coordinate systems a lot of times, and sometimes you can make a problem quite a bit easier by choosing the right coordinate system. So what is an allowable coordinate system? I'm going to write coordinate system a lot, so I'm just going to always call it CS. Well, an allowable coordinate system for any math you do, I think until you start getting into, I think it's relativity where they sometimes start using crazy coordinate systems and stuff. But in all your engineering classes and stuff, an allowable coordinate system means a right-handed coordinate system. And the requirements for a right-handed coordinate system are the x-axis, the y-axis, crossed with the j-axis is equal to the k-axis. Now I'm going to skip down a line. I'm going to come back to the second one. the j-axis crossed with the k-axis is equal to the I-axis. And then the middle one, I left that because j always has to be a pain. So the middle one says I cross k is equal to j, right? No, it's equal to negative j. And so if you ever choose a coordinate system and it doesn't have these properties, then your coordinate system is going to mess up your vector math. Okay. I mentioned the right-hand rule before. Let me show you how to think about this in terms of the right-hand rule. So let's say let's use a coordinate system where the x-axis is this way, the y-axis is this way, and the z-axis is out of the page. So that's like looking at the tip of the arrow of the z-axis. Okay. And now start with your fingers on the x-axis, pointing in the direction of the x-axis. Rotate them until they're aligned with the y-axis. And that will put your hand in a certain configuration, a certain orientation, okay? And in that orientation, if you stick your thumb straight out, that's the direction of the z-axis. So start here, rotate here. Your hand has to be in this orientation, and so the z-axis is out. Okay? And so that's the right-hand rule telling you that this cross product requirement is satisfied. Okay. If you tried to go the other way, like this, well, I guess this actually brings up sort of an important point about the right-hand rule, because you could do your fingers all the way around, but it has to be, you have to go the shortest angle from X to Y. Okay, so from here, you can't turn your fingers to rotate it to Y, so that hand orientation isn't going to work. The right-hand rule gets used all the time. You used it for a few things, I think. Well, in Physics 2, you'll use it all the time, anyone who's taken Physics 2. It always is a relationship between a rotation direction and a perpendicular vector. That's what the right-hand rule is always for. So really, I mean, this is not a perfect tool for using the right-hand rule. But, if the right-hand rule was the only reason we evolved right hands, this isn't what your right hand would look like, But this is useful for a lot of stuff, picking up forks and stuff. But really what the right-hand rule, really, this would be what your right hand would look like if it were optimal for this. It would show a rotation direction, and then it would just have a vector pointing perpendicular to it. That would be a cool pendant, actually. Like if you had that pendant, you could wear that, you could bring that into tests, and they'd have to let you because it's your outfit, and then you'd never have to use the right-hand rule again. Okay, anybody have any questions about that? All right, there are two important things that we're going to do with vectors. This is going to come up in statics all the time. two important vector calculations. The first one is calculating a vector from one point to another. And the second one is calculating a unit vector in a given direction. Okay, so first, a vector from one point to another. So if you are given or able to determine the coordinates of points A and B, a vector from A to B is just the coordinates of B minus the coordinates of A. Okay, so the first one in this difference is your ending point, and the one you're subtracting is the starting point. So it's just so easy, so nice and simple, and we're going to use this all the time. So what's a vector? What are the components of a vector from 3 to -1 to -6, -5, 4? So you start with the destination coordinates. By the way, this is kind of an aside, I guess, but I don't know. I remember feeling a little hazy on so coordinates of a point feel pretty different than components of a vector. And so it feels like I'm kind of, maybe to some people, it feels like I'm kind of glossing over something by treating coordinates of a point as vector components. But remember that what the coordinates of a point represent are the components of a vector that goes from the origin to the point. Okay, so really coordinates are a type of vector. And so you can always do vector math using coordinates. Okay, so the way to calculate this vector is -6, -5, 4, because that's the ending point, minus 3, 2, -1. And so -6 minus 3 is -9. -5 minus 2 is -7. 4 minus -1 is +5. Okay. And since these are coordinates, these would be length units, whatever units you're using. If you're in SI units, this would be in meters. And so the vector components would be in meters. Okay, so here's something that you've done before, but probably didn't emphasize this way of doing it before. So the moment of a force, or the torque, in other words, the way you calculate that is you define this rho vector, that's the Greek letter rho, that's equal to the coordinates of a point P minus the coordinates of a point A. So this is the coordinates of the location where the force is applied. And this A is the coordinates of the about point, which in your physics 1 calculations would have usually been like a hinge or something like that. So the coordinates of where that hinge is. And so the meaning of this is that that rho vector goes from the hinge, from the about point, to the place where the force is applied. And this is how you do that calculation. And I just want to do this one time here. This is the calculation we're going to do the most with vectors in this class. So let's say you have a hinge here and you have a rigid body. And there's a force being applied. And let's say that this force vector is 100, -40, 0. And that's in newtons. And then let's say that the about point, it has coordinates 4, 2, 0 in meters. And then the location where the force is applied has coordinates 6, 3, 0 in meters. What's the moment produced by that force about the hinge? Okay, so in most physics 1 classes, the way you would do this most of the time is you would either, instead of being given these 2 points, you would either just be given an angle that this is at, or you could, use inverse trig and calculate what that angle is. But then you would just use sine and cosine and come up with the components of that force and calculate the torque that way. I think that's probably what you're a little more familiar doing right now. But we're going to do this as a vector calculation, just all in one step. Okay. So the row vector is the coordinates where the force is applied, 6, 3, 0, minus the coordinates of the about point, so 4, 2, 0. And so that row vector is 2, 1, 0. And this is in meters. And then the moment of this force around that about point is the row vector 2, 1, 0, crossed with the force vector 100, negative 40, 0. And the vector you get out is 0 here, 0 here, and then negative 80 minus 100, so negative 180. And this is all in Newton meters. Okay. Speaking of this in terms of moments, we'll spend more time on this obviously pretty soon. But what does that negative tell you? I mean, it's a vector component, so it tells you that the component is in the negative z direction. That means that if we're looking at this with the z-axis coming out of the page, our thumb is going into the page. And so that rotation that's caused by that force is this, according to the right-hand rule. So a negative moment component always means clockwise if you're sort of looking down the barrel of the axis. Okay. And it makes perfect sense that that force would make this rotate clockwise. Okay, so this is if we want to calculate a vector from one point to another. You just do that subtraction. Just remember that it's always the ending point minus the starting point, not vice versa. So if you want to be disciplined about it, just remind yourself to think of it not as a vector from A to B, but as a vector to B from A, And then the other thing that we're going to do a lot is we're going to use unit vectors. I'll charge my stylus. So unit vectors in a given direction. And there are two ways that we're going to do this. Before I get into that, remember that I said that a vector is equal, is a magnitude and a direction. And so the idea of a unit vector is that we break up this vector into the magnitude of the vector multiplied by a unit vector that defines the direction. I'll say this is a unit vector representing a direction. And this is going to come in really handy to us because the main reason that this is going to be useful is because there are going to be a lot of cases where we know the direction of a force, but we don't know the magnitude of the force. And so by writing the force vector this way, we'll be able to reduce the number of variables that we need to represent that force. Okay. Like if you're working in 2 dimensions and you have an unknown force vector, that's 2 variables. You don't know X or Y. But if you know the direction, you just don't know the magnitude, then you can write out the direction as a unit vector and then just multiply it by a single unknown variable representing the magnitude. And you've cut your number of variables in half. And in a lot of cases, that's going to be the difference between being able to solve your system of equations and not being able to. Okay, so there's 2 ways to do this. 2 ways to calculate the unit vector. The first one is if you're given a reference angle in 2D. So if you're given a reference angle in 2D, and it's important that this really only works for 2D. There are ways you could extend it to 3D, but it's complicated enough that it's not very helpful. We'll just use the other approach for 3D stuff. So if you're given a reference angle in 3D, all you do is find the counterclockwise angle from the positive x-axis to the vector. The vector has to have its tail at the origin. And then the unit vector, so my variable name for this vector is going to be u. I'm going to use this little hat to represent that it's a unit vector. Okay. And it's just equal to, so the counterclockwise angle theta from the positive x-axis to the vector. So the unit vector is just going to be then the cosine of theta, the sine of theta. I won't even write a z because we're only going to use this when we're in 2D. And the second way to calculate a unit vector is if we're given starting and endpoints that are in the same direction as the unit vector, and this is good for, you can use this in 2D and you can use this in 3D. This is always the one you're going to use if you're in 3D. So first you would calculate a vector that goes from one point to the other. And you would do that, just by subtracting the coordinates. Then you would calculate the magnitude of the vector u that you just calculated. And you do that using the Pythagorean theorem. So that's the x component squared plus the y component squared, square root. And then the unit vector is just 1 over that magnitude times the original vector. And I'll do examples of both of these. Okay, so for the first one, let's say that we have a vector with a magnitude of 30 meters. And let's say that the direction of this vector, if this is our coordinate system, is this way, where this angle is 20 degrees. Okay, well, this is in 2D, and we're given a reference angle. So in that case, we're going to use the first one of these two approaches, the cosine and sine approach. And so what's the counterclockwise angle from the positive x-axis to this? So it's 90 to get here, 180 to get here, plus another 20. So that's 200 degrees. And so the unit vector is cosine of 200 sine of 200 I knew what that was. So 0.940 and then negative 0.342. Of course, you could also, break it up into a right triangle and then think about what quadrant you're in for the plus minus signs. But this always works, and I like this because it's really easy to translate into computer programs, and most of the calculations that we're going to be doing in these engineering classes in a professional environment, you'd really be putting those into a computer program. So you kind of want techniques that can be put into an algorithm. Okay, so now that we have this unit vector that's going in the right direction, how do we come up with a vector with a magnitude of 30 that's in that direction? Well, the whole idea of a unit vector is now we can just take that unit vector and multiply it by the magnitude we want. So the vector we want then is 30 times this. And you get negative 28.191, negative 10.261. And this is in meters because the magnitude was in meters. Okay. Any questions about that? Okay, so this way of doing it with cosine and sine, really only useful in 2D and really only useful if you're given some reference angle. Yes?
You got 30 from the length?
Yeah, that's right. the vector magnitude was 30, so we just multiplied it then to the unit vector. Okay, so let's do another one. So now let's say we have a force vector that points in the direction from the coordinates 2, -1, -4 to the coordinates -6, 3, 3. And instead of knowing what the magnitude of the force is on this one, we're just going to represent the magnitude as a variable. I'll call it T, like it's, in this case, it would be a cable force. So it has the unknown magnitude, capital T. All right, well, I'm going to draw a picture of these. This is just a two-dimensional kind of projection picture, but like these might be our 2 points. This would be the one -6, 3, 3. This would be the one 2, -1, -4. You can imagine that these are like the 2 pulleys that the cable extends between. Okay, and that's why this cable force we know is going to act along that line. But we don't know yet what the magnitude is. We're going to have to use Newton's laws to calculate that. So we have a vector that points along that line, but it has a magnitude of T. Okay, so the way I'm going to calculate this vector is I'm going to calculate, well, first, which technique do we want to use? We're not given an angle. We could maybe figure out the angle, but really just the fact that these are 3-dimensional vectors means we don't want to mess with that. So I'm just going to go straight to the approach where first I calculate the vector that goes from 2, -1, -4 to the other one. So I'll call that my vector U. So this is -6, 3, 3 minus 2, -1, -4. And so that's -8, +4, +7. And then I'll calculate the magnitude of that. So this is equal to 8 squared plus 4 squared plus 7 squared square root. And that comes out to be 11.358. Then I'll just divide each component of my U vector by this magnitude. And so my unit vector is 1 over 11.358 times the vector negative 8, 4, 7. And you get negative 0.704, positive 0.352, 0.616. And then that's the unit vector pointing in the direction of that red arrow. For our, kinetics problem, we didn't want that. We wanted to represent this force in terms of its unknown magnitude t, but now we just have to multiply that vector times t. So our force vector is just t times u, and so this is just negative 0.704 times the variable t, 0.352 times the variable t, 0.616 times the variable t. And then that's the force vector that we would put in Newton's second law or use in the moment equation to do our kinetics. Any questions about that? Yes?
So that's the final answer.
That's the final answer, yeah. And so it's sort of an unsatisfying final answer because it has an unknown thing in it. But then we would plug that into like Newton's second law, do the math, and then be able to calculate t from Newton's second law. And we'll do a lot of that once we get into particle statics. Any other questions about that? Okay, so that's kind of the greatest hits, highlights of the vector review. I'm going to give you a vector review to read. If it feels like too much of a review, feel free to skim it. Just get what you need out of it, and then I'll give you some problems to work on from the vector review. Okay, that's all. Goodbye.